In this video, we're going to talk about density curves. Let's start off with an example, shall we? Let's say we've got a friend, her name is Selena, and she works at a bookstore at an airport. Now, she loves to be efficient and get to work as quickly as she can, and there are some options in front of her. So when she gets to the airport, she normally has taken a train within the airport to get to the bookstore, her place of employment. But the airport just opened up a walkway, which on a good day should take her about 4 minutes to walk to the main terminal, to the bookstore. So really, is the train or is walking faster? So our stats-loving friend, Selena, she collected 1,000 workdays of data. She timed how long it took her on the train to get to the bookstore. And so she compiled the data, or someone did, into this dot plot here. So all the red dots are the amount of times that it took less than 4 minutes on the train, and the blue are 4 and greater minutes to get to the bookstore. So what we could do is we could count up the number of red dots and divide it by 1,000 and multiply that by 100, and it would give us the percentage of days where it was faster, right, because less than 4 minutes, it's faster to take the train instead of walking down that lovely brand new walkway. I don't know if you've ever counted hundreds of things like tiny little dots, but there's got to be a faster way. And there's something called a density curve. So the leap from this dot plot to this density curve isn't a crazy one. So really, we've got two different color shaded areas. This reddish orangey one, I don't know why it's not more red, represents all those red dots where it's faster to take the train. And then this blue bit over here would be all the dots where it is not faster to take the train. So one thing you might be wondering about is, what are the rules of a density curve? So if you look, we've got from 2 to 5 minutes, because that was the shortest amount of time that it took for the train to get there and the longest amount of time, according to her 1,000 data points. And we still have the 2 to 5 here. We still have the label down here, journey time in minutes, the same. But then we've got this height thing. So we want to represent 100% of these data points, right? We want to represent all of the data, 100%. So if we take 5 times 2, because this is going to create a rectangle of sorts. So 5 minus 2, that width, or that base, is 3. So the height needs to be multiplied by some number to give us 100%, or 1. So that is where we get a height of 1/3. And the area and all the squares and things will make, hopefully, more sense by the end of this video. So all that being said, cool, a dot plot is great, but a density curve might be better, especially when you have 1,000 data points. So what is a density curve? Well, it has two main components. It's essentially a shape. It's called a curve. It can be curvy, but it's mostly rectangular because you can find the area of base times height way easier with a square. Anyway, it's always on or above the horizontal axis. So it's got to start either here and be above. It's got to create a shape. Otherwise, it's nothing. There's no curve. And it has to have an area exactly of 1 or 100%. Because, same thing from this example to this example, we wanted 100% of the data points, whether they're the same. For example, they'd all be the same color, or they're very different, where we'd have multiple colors. Also, another point is that the area under the curve, or area, this whole shape, really, and any above the interval, so for example, from 2 to 5 minutes, estimates the proportion of all observations that fall in that interval. So if we wanted to find the area of this entire thing from 2 to 5, that's 3 times a third. That's 100. That represents 100% of the data points. But what if we wanted to find the proportion or the percent of the red dots, which is what Selena was baffled by at the beginning of this video. So what's easier, instead of counting up all these dots, is finding the area of this red, orange, orange? Yeah, this orange square here. So really it's finding the area. As long as you have accounted for that height, right? So 3 times a third makes 1 or 100%. So from 2 to 4, that's a distance of 2. So 4 times 2, that's our base, right? We multiply by the height of 1/3. 2 times a third is 2/3. So 2/3 of the time, it's actually faster to take the train to work. In a percent, we would say that we can estimate that it's best to take the train to work roughly 67 or 2/3% of the time. Look at that. We solved Selena's problem and we learned something new in the process. Oh, wow. Now, what might feel so random in the middle of this video is talking about random numbers, but you know what? They have a place. They do. Let's work through another example where we are looking for a random number generator to produce a number between 0 and 2. And if you were thinking, whew, 1, this random number generator is producing numbers like 0.84522 and this thing. So all the numbers. So let's say that random number generator will spread its output uniformly across the entire interval from 0 to 2 as we allow it to generate a long sequence of random numbers because, gotta give a computer something to do. Let's do 3 things. Let's draw a density curve to model that distribution of random numbers. And then about what percent of those randomly generated numbers will fall between 0.87 and 1.55. Talk about more randomness. And then let's estimate the 65th percentile of this distribution of random numbers. First thing that we are tasked with is creating that density curve, or really that density rectangle. So it always starts with a horizontal axis, which will go from 0 to 2, because that's the range of our numbers that we can produce. And then there's always a thicker bar up top. I made that a little thicker so you could see it, why it's orange. I don't know, just felt like it. So I'm going to label this horizontal axis from 0 to 2 and title it, which will be random number. And then this doesn't necessarily have a axis label, but we do need to figure out the height. First things first, labeled our horizontal axis here from 0 to 2, labeled it random number because that's what those numbers represent. And so lastly, I want to find the height here. And so if we have a width or a base of from 0 to 2, so that is a width of 2, and I want this thing to be equal to 1 or 100%. So 2 times what gives me 100%? And it's going to be a fraction, especially if this is a whole number or a number larger than 1. So that means the height is 1/2, because 1/2 times 2 is 1. So from here, we can figure out what percent of the randomly generated numbers will fall between 0.87 and 1.55. So what I'm going to do is find 0.87 and 1.55 on here and create that rectangle and figure out, what is that percentage? Of course, this is not drawn to scale, but I cut this in half to find 1, cut it in half again to find about 0.5 and 1.5. So this pink square here, rectangle actually, is from 0.87 to 1.55. So let's find the area of this pinkish square, rectangle, thing. So I'm going to use my base times height. So I want the difference between 1.55 and 0.87, and I'm going to multiply by the height that we found in the first part as 1/2, and that's about 0.34. So 34% of those randomly generated numbers will fall between these 2 values. So the last part of this problem asks us to estimate the 65th percentile of this distribution of random numbers. So that's working backwards, where we're not trying to find the area. We have the area. In fact, it's 65 or 65% or 0.65. So we need to figure out from 0 to what is the area 1/2 times that number, that x value, create an area that is 65. Let me show you. So I've drawn just a random base length of a yellow rectangle this time. So I want to know what this x value is that creates an area of 0.65. So using that area equals base times height equation, we've got our area, which is 0.65, and that's going to be equal to the base, which is x minus 0, so that'll just turn into x times its height. So let's figure out what that is. So our equation becomes 0.65 is equal to 1/2 x. These 2 little slashy lines mean due to both sides, so we're going to multiply by 2 to both sides, and that means that our x value, this number, where 65% of the numbers fall less than that number, is 1.30. Woo! So what happens when our density curves actually look like curves and less rectangles? Well, we describe them in the same ways that we talk about distributions of a quantitative variable. So that means that we would look for any kind of symmetry. So, right, this one, for example, is roughly symmetric. It's got double peaks. If you cut it down the middle, it kind of mirrors itself. And then, of course, we've got our skew to the left, where our tail is to the left. We've got a single peak. Skew to the right, we've got the tail to the right here. We've got single peaked. So that should look familiar, and you would describe density curves in the same way that you would describe other distributions that look like this. And our other measures of center and variability apply to our density curves as well. Yay! So, as a reminder, we've got our mean of a density curve. So that's the point at which the curve would balance if it was made of a solid material. So think of it like a balance beam of sorts. So these figures represent, all right, what is the mean really doing here? So the mean here, that's just not going to work. That's going to tip over that way. Is the mean over here? Nope, it's going to tip. Is the mean right about here where it balances out? Yes. So the mean of a density curve is its balance point. And of course our other measure of center is our median. And so that is the equal areas point. So that's the point that divides the area under the curve in half. So if we have a roughly symmetric curve here, the mean and median will be in the same point, right? This is balanced and it's smack dab in the middle. Area to the left and to the right are pretty much equal. But when we have something that skews to the right, we've got a tail over here to the right and a bulk of the data points are over here to the left, what ends up happening in a right skewed density curve is that the mean is pulled away from the median. So the median right here, is smack dab in the middle. The area here and roughly right here are equal. The mean gets pulled away from the median towards the tail. So that happens in a right skewed density curve. Were you expecting this slide to be about the left skewed density curves? Well, it is, kind of, but we're going to have to work for it. So let's work through an example to figure out what does the left skew do. So let's say that we have this density curve here that models a distribution of quantitative data. Identify the location of the mean and the median by letters. So we've got this letter here, A, we've got B, and we've got C. Which one is the mean? Which is the median? Let's figure it out. So here are some things that we know. We know that the mean is the balance point. So at which of these points, if I was going to put a little triangle underneath it, would it balance? Would it look like a balance beam, right? But a nice balanced one. All right, enough of the word balance. The median cuts the area in half. So looking at this right here and how it's skewed, I could for sure rule out C because this area is less than this area. Also, we know that a right skew curve, the long right tail over here pulls the mean to the right. So it pulls the mean towards the tail. So I have a feeling that mean is not going to be C either. It's going to be pulled towards that tail if it behaves like a right skew. So here's my thinking. I'm going to say that the mean is A and the median is B. Now, we know that C wasn't an option. That just didn't make any sense for either mean or median. Now, here's the thing that helped me determine which one was A and which one was B. It was this idea from the last slide. So we happen to know that in a roughly symmetric, the mean and the median are right down the middle. They're in the same place because remember they're measures of center. But here, when we have a skew, the mean gets pulled towards that tail. So to me, if this was roughly symmetric, the very middle line, actually C, would be the mean and the median, but it's not. Again, no C. So that must mean that the median is further inwards or further from the tail than the mean is going to be. Because remember, the mean got pulled away from the median towards the tail. So that must mean the mean here gets pulled towards the tail. It's got to be the leftmost line. So the mean is going to be A, which means that the next line, and the only one left, is B, our median. They can't be the same line in this case because of this as well, because it's not roughly symmetric. So mean is the leftmost line here getting pulled towards the tail. Median is that line right next to it. That's going to make that area to the left and the right hand side roughly equal. All right, I've played enough practical teacher jokes on you today. That's going to do it for this video. Thank you for watching.